Hello, everyone. Welcome, everyone, to this FlowJo webinar this morning. Good morning, everyone, and welcome to this high-dimensional data analysis workflow in FlowJo version 10. So today we will be talking about FlowJo version 10. As some of you may know, we do have a new version of FlowJo that was released in last May, and that's FlowJo version 11. So some of the tools that I will show you today are also available in version 11. So just stay tuned for more webinars on that. I'm Serena Di Cecilia. For those of you that don't know me, I am the software solution manager in EMEA. And here you can find my email address. So let me get a pointer. Okay. Please feel free to email me if you have any question or if you have any problem with FlowJo, if you need to troubleshoot something, or just if you have any curiosity question, I'll be happy to take that. Okay, so today we will go through a different workflow. So instead of analyzing the data with a conventional flow cytometry gating strategy, we will go into something that is less conventional. So first of all, let's define what is conventional gating strategy or conventional analysis and why is that hard. Okay. So let's imagine of having something like this. This is a 27 colors, 27 parameters, plus two physical parameters. We have 29 different parameters panel that allows us to characterize all the different human immune cells. So let's imagine we want to characterize our cells by using primary markers in blue, secondary markers in pink, and tertiary markers in orange. Now, the first thing that we need to clarify is the panel design. So first of all, we need to make sure that the panel that we design is actually correct and includes all the markers that we need to characterize all the different subpopulations. Just to give you an information, if you are willing to get some help on panel design or get some insights on what can be your panel to characterize your populations, we do have available BD Research Cloud. There are several webinars on that. This is a cloud environment tool that allows you and helps you in designing the panels for your characterization. Now, today, this is not a webinar about panel design or BD Research Cloud, but just to give you an information, if you navigate through the website, you will find a page dedicated to BD Research Cloud, which is free and accessible for everyone that has a portal account, which is as well free. So just to mention that you do have some resources that you can access to in case you need any help or any input in defining your populations or designing. Because what we will look at today is an analysis from a different perspective. So we will be using algorithms to analyze our data. So we will go from cleanup to clustering characterization by using algorithms. And the moment we use algorithms, having a good panel is actually way more important than when we do a conventional data analysis. So starting from this panel, let's consider that we want to start analyzing one population of cells, for example, the Tregs. So in order to analyze this population, the conventional gating strategy, what asks us to do, it's something like this, where we start by creating a time gate and then gating on our CD45 cells, then isolating our single cells, our lymphocytes, then the CD3 population, and then going deeper and deeper and starting with CD4 positive. And then finally, we get our populations of Tregs by looking at the CD25 positive, CD127 low. But since we have tertiary markers, we can actually analyze subpopulations of Tregs. So just to do this in a conventional way, we need to draw 10 plots or 14 plots or more. But also when we move into the rest of the populations that we can characterize, we actually need more than 10 plots. But this panel right here allows us to characterize also other populations of cells, not only the Tregs. So how many plots do we actually need to draw in order to look at all the possible combinations of markers and make sure that we don't miss any combination and we don't miss any population? Well, we have different parameters. We actually do have, this is related to a different panel of 16 colors, and apologies for that. But overall, what happens is that we have a high number of parameters. And if we want to look at all the combinations of markers, we need to draw multiple plots. And then when we start gating on each individual plot and we spend, let's say, 2 minutes on each plot, these will add up time to analyze the data. And at this point, the amount of time that we need to analyze the data, it comes to 8, 10, 12 hours of that analysis. Now, there must be a better way to do that, and there is a better way, which is what we are going to look at today. This better way, it's given to you from algorithms. So we do have algorithms in FlowJo, and they come into different forms. They can either be embedded into the software, which means that they are already into the software. So if you do have FlowJo version 10.10, you will find an algorithm tab where you can actually find several tools in there. And another form is considering plugins. So plugins are basically algorithms that can extend the functionality of FlowJo. So what are algorithms? This is a general question that I get, are just calculations. So calculations that extend the basic functionalities of FlowJo. So they can either be into the software or they can be added to the software as plugins. Now, you can find all these plugins on the FlowJo Exchange. If you ended up on this webinar, it means that you sign up to the webinar, probably through the FlowJo webpage or through some social media posts. But overall, you had to end up onto our website. And so if you just navigate to the website, you will see that there is a FlowJo Exchange page where you can find all the different algorithms that are available there. So first of all, let's see how we can make the jump from our conventional data analysis into high dimensional data analysis, which is basically making our bias analysis to less biased. So what can we do with these algorithms? First of all, we can use algorithms for cleanup and normalization. So the first thing that we need to do on our data is clean them up. We cannot feed the algorithms with the raw data. We actually need to make sure that whatever we have is actually good. So we need to clean up the data, and eventually we may need to go through a normalization step. So for cleanup and normalization, you see here a list of plugins, or list of algorithms that we have available. FlowAI, FlowClean, Peacock, FlowCat, these are all algorithms that help you to clean up your data from fluorescence anomalies. So today, you will see in this list right here that I'm going to show you, the ones in black are the ones that I'll be using. But just for you to know, we do not only have the algorithms that I'll be using, but all the ones listed here plus more. If we ever have the need to normalize the data, we can use cytonorm, cycombine, or MNN. And on our website, you will find different combinations of algorithms to do this workflow. That's because there is not a specific set of algorithms that we recommend you, but you can mix and match them. You can choose which one better fits your needs. That's the overall or the end goal point. So you may want to be able to try all of them and then pick the one that better fits your data and better fits your needs for your analysis. Once we have cleaned up the data, we move on to the next step, which will be dimensionality reduction. So we were talking about 27 parameters before, or 16 parameters, or 10 parameters, or 5 parameters. But in order to analyze this number of parameters, or easily called colors, we need some help. Our brain actually cannot see all these dimensions, cannot see all these parameters. And so what algorithms do during the dimensionality reduction step, it's basically reducing all the dimensions that we have, reducing all the parameters that we have into a b-dimensional space. And the reduction to the b-dimensional space actually allows us to see the data, to finally see the data. So for dimensionality reduction, you see here listed several algorithms: tSNE, UMAP, EmbedSum, TriMap, PeacoQC, FATE. These are all algorithms that perform dimensionality reduction and will allow us to visualize our entire dataset into a single b-dimensional plot. So today we'll be using tSNE. And you see it here with an asterisk because tSNE is already embedded into FlowJo. So you can already find that there. Once we have reduced the dimensions, we may take advantage of automated clustering tools. And the advantage of using automated clustering tools are several in the field. So we could think of using automated clustering tools because we want to speed up our analysis. We know really well our data set, but we want to make sure, that some calculations from the algorithms or that the clusters that we have are actually defined from algorithms. And in that case, we could use FlowSum, for example, or we in the case of today, we want to explore all the possibilities that are present in our data set, and in that case we could use, for example, Phenograph or Xshift. So I'll be using Xshift today, but just as you know, there are FlowSum and Phenograph as well that are automated clustering tools, and then we have some other semi-automated clustering tools like EasyDuffy, FlowMeans, that use a training data set to generate your clusters. And again, there is a webinar specific on that in case you want to go deeper into that. After we take advantage of automated clustering tools, we may want to characterize our clusters, and so we may want to explore our clusters deeper. So we want to phenotype them or isolate them and so on. So in this webinar today, I will be using Cluster Explorer to explore our clusters, and then Euclid to validate our clustering results. But just again, as you know, just for you to know, we do have some other post-clustering analysis tools, such as BioLinbox for visualization, or MEM for clustering labeling, or embed to embed your clustering and dimensionality results into new samples. So just let me open up the Q&A box just in case there's any Q&A that come up. Okay. So what is the workflow? What should we do, and where can we find an actual workflow, or what can be some steps that we can follow? So we will start with data pre-processing. So we need to prepare the data for the algorithms. As I was mentioning before, we need to make sure that whatever we feed the algorithms with is actually including good quality data. So we will go through a pre-processing step. Then we want to perform dimensionality reduction in order to be able to visualize our data. And then we want to cluster our data, phenotype them, and eventually compare and validate our clusters. There is another extra step that I will see if we have time to go through in order to further characterize or visualize the results. Okay, so let's start with data pre-processing. So for data pre-processing, there are several things to keep in account. The first one is that we need to either compensate or unmix our data. So depending on the instrument that we have, if you're working with conventional flow cytometry, we want to compensate our data. If we are working with spectral flow cytometry, we want to make sure we unmix our data. Now, for this step, there are several tools available in FlowJo. So you have a compensation wizard that can help you to recreate a compensation matrix when in conventional mode, or to unmix your data when in spectral mode, as well as we have the ability to use autospill, autospread as an algorithm to facilitate the compensation process. And again, there are multiple webinars specific on compensation, so I will not focus on this today, but just to give you an overview of what you need to do. So we can then compare different matrices, we can calculate spillover spread matrices, total spread matrices, cosine similarity matrices, and so on. All these tools will give us information regarding the quality of our panel in general. So we can see if we do have spread in our panel by using, for example, the SSM, and then consider or reconsider eventually some fluorochromes versus others for some specific markers. So after we make sure that we either compensate or unmix, we want to make sure to correctly transform the data. So we want to see all our data into the graph space. So as long as we keep our data within the graph space and we don't have events that are falling outside of the scale, we are good to go. The reason why we want to correctly transform and scale the data, it's because the algorithms perform their calculations in the graph space. So whatever is outside of this area, it will not be taken in account from the algorithm or could impact the overall results. So please make sure you correctly transform and scale your data. Once we have done these two steps, we then can proceed with evaluating the signal stability of our acquisition. So basically, we want to make sure that during the acquisition, there were no alterations of the flow rate or the signal stability. And what we normally do is something like this, where we perform a manual gate, manual time gate. We remove some area of the space where there may be some fluorescence anomalies, and then we go on. In this case, since we are using algorithms, we are not going through this step of creating a manual gate on time, but we will be using automated cleanup tools that will give us two different populations. One of bad events, which includes all the anomalies were automatically excluded from the algorithm, either because there was an alteration of the flow rate or the signal acquisition and so on, and one population of good events, which are the events that are considered reliable and the events that we can proceed using during our analysis. So all these tools are available in FlowJo. I will be focusing on Peacock today, or I'll be using Peacock today, but just to know, there is one specific webinar on quality check and normalization if you want to go deeper into all the different options that we have. Once we check the signal stability, we then go into one crucial step, which is the removal of irrelevant events. So please remember that clean up your data by using algorithm is not sufficient to process your data for the algorithm. So in this pre-processing step, it's true that we clean up the data from fluorescence anomalies, but we will as well need to clean up from everything that is not relevant to our analysis, such as, for example, doublets or debris or dead cells and so on. So this step, it's called removal of irrelevant events, and then we can finally move on to the next steps. Okay, the next step, so once we have prepared the data with these initial steps, we will then perform one extra step to allow us to characterize each individual file, or eventually to perform the different comparisons that we need to do. And this step includes annotation and concatenation of the data. With the annotation, we want to label our samples. We want to characterize each individual sample. Let's say that we are comparing control versus treated. Then at this point, we will need to label our control as controls and our treated as treated. So this way we can then backgate each individual condition to the overall results. And then we will move into this step of concatenation. So basically we will create a single FCS file starting from multiple as files that we want to compare. So I see there may be something in the Q&A already. Okay. What algorithm would you recommend to transform data, BiExp, ArcSynH, or something else? Well, bi-exponential, ArcSynH, or something else are not actually algorithms, and there is not an algorithm in FlowJo that tells you or that automatically transforms your data. So this actually depends, like, first of all, depends from the parameter. If you have physical parameters, you know that you need to look at your data on a linear scale. But if you do have fluorescent parameters, then you can either use bi-exponential, ArcSynH. So that's up to you. I personally prefer to work with bi-exponential, but both of them, if correctly transformed, the scaling, it's either bi-exponential or ArcSynH. They should all give both good results. So it's not, I mean, I personally do not have a preference for that, but it's an important topic. And you can also perform both, let's say you can test the algorithm with both ways and see, you know, which one better fits your data. That's the important thing. Okay. Can you go back to the data processing slides? Yes, I go. Should compensation also be processed? Okay, I don't know what this question means. Data pre-processing slide, I believe it's this one, but I don't understand what is this question related to. Should compensation also be processed? Compensation should be done, processed in terms of quality check your compensation controls. You can do that if you feel that there are alterations of the flow rate or the signal acquisition during the acquisition step, but technically you may not need to do that. Okay, I hope I've answered questions up to here. Okay, so then we will move into dimensionality reduction. So we create a single FCS file starting from multiple FCS files that we want to compare, and then we move into dimensionality reduction. Okay, so remember this panel that we had before? When we look at it, let's say from a conventional data analysis way or point of view, what we have is that each population is actually defined from multiple histograms or from multiple plots and so on. So now this looks like a really high number of plots. And instead of looking at our data this way, we can look at our data from a low number of dimensions, which is basically by using dimensionality reduction algorithms that can be tSNE, can be UMAP, and so on. So instead of having multiple plots to show our data, we will have only one single plot and only two dimensions, y and x. So these will be our new dimensions when we reduce the number of dimensions from 27 or 10 colors or 15 colors to only two dimensions. Once we have performed dimensionality reduction, we will move on to the clustering analysis. Now, today we will be using Xshift as an automated clustering tool, but if you look at all the webinars that we have for the advanced workflows, we have a combination of tools. So if you're interested in something else, let's say FlowSum or Phenograph, for example, there is for sure out there one of the webinars that is using one of these other two algorithms within this workflow. So just to mention that the one that you choose, it can depend from your data set, from your overall goal, and from your starting point as well. I see one beautiful question, which is, can we include forward and side in the calculation of dimensionality reduction and clustering? This is a really challenging question and a really frequent question as well. I would say it depends if you actually find useful information by using your side scatter, for example, rather than the forward, and include it in there. from my personal point of view, in the way we or I analyze the data actually includes a pre-processing step, the removal of irrelevant events, which is based already on forward and side scatter. So basically, I do not take cells, when we look at forward versus side, I take my cells, I exclude all the outliers or the marginal events, and I move on. So depending on the data analysis that you are performing, if you feel that a side scatter value can give you insights and can give you more information in the dimensionality reduction and clustering analysis, yes, for sure, go for it and include your physical parameters as well. But in the majority of the cases, even to reflect our conventional gating strategy, you may not need to insert or to use or to include your forward and side scatter into the dimensionality reduction and clustering tool. Okay, so for clustering, today we will be using Xshift. Xshift is a really, really fast algorithm that is available within FlowJo. It is available as well embedded in FlowJo version 11. So in case you want to try this kind of workflow in version 11, you will find that. There are several pros of this algorithm. It's really precise and find a large number of meaningful subtypes. Is optimized for small and rare populations, so it actually finds really, really small population compared to other algorithms, and does not require you to input the final number of clusters, which means that the number of clusters is defined automatically from the algorithm itself. So this can be either a pro or a con depending on what you need. Okay, so if you already know how many clusters to expect and you use Xshift, it will give you probably a different number and you may be, disappointed with that. So in that case, in case you know already how many clusters do you expect from your analysis, I would recommend you to use FlowSum for your analysis. So that's why, like, using these algorithms, it always depends on your question. Like, what is your question? What do you want to get an answer for? And what is your pre-knowledge about your data set? Okay. So once we get the clusters from clustering algorithm, we will perform another step, which is cluster evaluation. So basically cluster results quality check. There is a specific webinar on this, which is really, really beautiful and goes really, really into detail about that. But overall, as a general message, what do we need to do when we actually generate clusters automatically? It's to evaluate the quality of these clusters, because most of the algorithms tend to overcluster, and so, or in some cases underclustering. So we have to find the balance between overclustering and underclustering. And Euclid as a tool gives us two meaningful results, two meaningful values, which are cluster check, Taylor index. So basically, you have two useful information from this tool. One is to evaluate if there are clusters that are really similar and they could be part of the same population, or clusters that are really different and they for sure are biologically different. And another information that you get through the modality score is the quality of the cluster itself. So basically, if a cluster should be divided into two or not, because there is a bimodal distribution of one marker compared to the rest. So this information actually evaluate the quality of your cluster's outputs, and it's important to perform this step just to make sure that we are actually looking at biological clusters or something that is biological meaningful. Of course, after this step, even if you find new clusters, the actual validation in terms of experiment needs to be done. So we always recommend to biologically validate your findings. So if you find a new population, we are all super happy and supportive for you, but please validate that biologically. Eventually, you can sort out that population, you can make sure that actually exists. You can put this population in the sorted cells in culture. You can do knock-in, knockout. You can do sequencing. There are many things you can do after that, but please make sure that the actual population that you find is actually real. Okay, and then we will move on to phenotyping. So once we have defined the clusters, we have to validate it, our clustering output. We can phenotype them so we can see what is expressed on the surface. We can filter out the cluster of interest. All of these can be done by using Cluster Explorer. Cluster Explorer will give you one bar chart that shows you the size of each cluster from your clustering output. It will give you a heat map that shows you all the different clusters and the expression of the different markers for each cluster. It will give you an overview and an overlay of all your clusters with dimensionality reduction coordinates. So if you do have tSNE or if you have UMAP, you can actually overlay your clustering results with that. And then you will have a line chart where each line is a cluster, and on the x-axis you can see the markers that you have in your panel, and you can see the values of expression of all of them. So basically you can use this line chart to filter out the cluster of interest based on the expression of the markers. So once we have phenotyped the clusters, then what we want to do is actually compare them. Maybe, depending on your question, again, like what do you want to do in your analysis, I can give you some ideas during this webinar. But one of the frequent questions that we have during our project is how things are changing from one condition to another, for example. And you can do that in Cluster Explorer as well. So you can add extra columns to characterize the abundancy of each cluster for each of your conditions or treatment or time points and so on. If you want to go even deeper, and I'm not sure we can cover this during this webinar, but there are webinars as well covering that. There is an extra step that you can do, okay? So we can all be happy till here. We can compare our clusters, we can see how are they changing over time and so on. But if we want to go deeper, we want to have a different visualization. For example, we want to get some specific statistics. We can go into the extra step of data visualization. So in this case, we can use, for example, violin box that gives us violin plots that shows us the distribution of the marker for each population. We can create correlation plots and see how two markers are correlated with each other. We can create different heat maps, bubble heat maps, but we can also create populations comparisons. So we can see if, for example, one marker, the expression or the difference in expression of one marker within different populations is statistically significant or not. So this is one of the ways we can analyze the data. We can create as well FMI tables, tables out of these. And all of these outputs are exportable, so you can download them and use them in your presentation, into your PowerPoint, and so on. And if you want to go even deeper, you can actually sort out your cells, or you can look at your cells by using one of the new instruments from BD, where you can actually see the cells. So up to now, what we have done is working with our classical flow cytometry analysis, but in this case, we can actually see the cells. So we can go one step further, add an extra layer of information to our data by looking at the actual cells. What you see here is just a differentiation between poor events and good events. So poor meaning like bad events, and you can see here how doublets and aggregates are shown as poor events rather than our good events, which are actually individual cells. So this just adds an extra layer of information to your data. But today we will cover a conventional flow, not conventional, but we will cover a flow cytometry workflow without imaging. Okay. So I hope there are no questions. So I will go straight into FlowJo and do my analysis with you. So if you don't know where to find algorithms, I see there is a question. Can all these things related to data visualization be done on FlowJo v10? Absolutely, yes. Everything is in v10. Data visualization for imaging as well is in v11. So whatever you choose. So where do you find plugin? Just to give you a quick information, if you want to start right now, I recommend you to go on the website, on our FlowJo website. You will find here FlowJo Exchange, where we have all the algorithms. And if you're just starting, I recommend you, especially if you have, well, if you have both Mac or PC, to download, search here for plugins and download Plugin Play. Plugin Play is a bundle that includes many plugins. So for Windows, we actually were more lucky. We were able to include more algorithms rather than for Mac. So, but you will find algorithms for quality check, for clustering, for dimensionality reduction, and so on. So my recommendation would be download Plugin Play if you want to start today. There is a PDF attached. Read the PDF. It's just one step for the installation and you'll be good to go. And if you do have any question or any problem, please reach out to me or the technical support available at flowjo@bd.com. So once you install the plugins, which is a copy paste step, it's nothing really difficult. So you can open up your FlowJo. I'm gonna open up my FlowJo v10. Okay, and I have it right here. So if you have downloaded Plugin Play and copy and paste it in the place that it needs to be, when you go under Workspace Plugins, you will find a long list or a list of plugins or algorithms that you can use. So you will find all of them under Workspace Plugins right here. So the first thing to do is to load our data set. So I'm going to add my data, sorry. Okay, FlowJo, add samples right here. And I have a folder that includes, it's called Training Data Advanced, is placed on my desktop, and I have 4 samples here. And I can load my samples. So you will see that I have 2 conditions of simulation. These are 2 patients. We're not going too much into the biology as we are actually doing a technical webinar today. So what we have is 2 patients labeled as PID1 and PID2, and then we have 2 conditions of stimulation, non-stim or TLR stim. So basically 2 conditions, non-stimulated or stimulated. So the first thing that I do usually in FlowJo or always in FlowJo is create my group. So I will create my group for my samples. So this will be my group. Okay, and I move my samples into there. Now, we mentioned about compensation and unmixing. So if you do not perform your compensation on the instrument, you may want to perform your compensation in FlowJo. You know you need to have your compensation samples in here, and so your single stains, and you can recalculate the matrix. However, in this example here, what I do have is another compensation matrix that I can use and I can apply on these samples that someone else did for me. So I'm just going to take advantage of that. So what I can do, and again, if you do your compensation in the instrument on the instrument and you see that everything is fine, just double check it, but make sure that you have double checked your compensation. So basically, this is my acquisition defined matrix. You see, I may have some issues here. So I was lucky, I do have another compensation matrix that I can add on top of this. So I can use the plus button from here and take my compensation matrix from the file, and it's right here, okay, into the same folder that I had. So I can open that. And now this is my new compensation matrix. If I want, I can compare my acquisition defined, which is basically what I had on the instrument, with this new edited compensation matrix. So I can, I can just overlay them just by multi-selecting them. You can change the color if you want to have something nicer, okay? So let's do this. Okay, and now you see that here I have actually solved these issues by using another, another calculated matrix from some of my colleagues. So I'm good to go. At this point, if I want to apply the new compensation matrix to my samples, I can easily do that. I can take the M and drag and drop it onto my group. Now you see that my samples have a new matrix and everything is fine. The next step would be transformation. I just want to make sure that all my data are correctly transformed. So I can start, for example, if you want, you can start looking at your parameters right here and everything seems fine. Okay, I'm not gonna go too much deep into that, but just to show you, in case you need to transform or to amplify or spread your by exponential or your arc-CNH, you will have the option right here to increase or decrease the width basis, which basically is extending this linear part of your bi-exponential axis. I see a question, which is another beautiful question. What is the correct way to name files and parameters? I know that some symbols may break plugins calculation. Can we use dot, comma, spaces, brackets? So the first thing to mention in informatics in general is that informatics do not know special characters. So please do not use special characters. I recommend you not to use dashes, or not dashes, yes, but slash, for example, or accents on your names and so on. So the the easier you name your file, the better it is. Of course, you're not going to name it A, B, C, D, E, but for parameters specifically, it's important to keep coherence within your experiment. So if you run 2 samples today, you label your experiment, your parameters in a way, and then you run your samples again in other 2 days, please use the same labeling for your parameters, for your staining. Always keep coherent your labeling, because this is extremely important. Okay, so now FlowJo is asking me to save the workspace because I have the auto-saving active, so I will just say yes. Okay, so once you have evaluated your transformed correctly, you can then start the QC of your data. So in this case, as I mentioned, I'm going to use Peacock for that. So I can just go under plugins and use Peacock right here. So I will have all the parameters. And since I modified my compensation, and as well, Peacock will always work with what we call comp parameters. So this will be automatically selected from the algorithm. And then you can choose to remove margins or not. I personally don't like I personally do not use this function of remove margin, as I remove the marginal events when I do my gating on the physical parameters. You can also choose to add QC images to the layout, so you can get your images right there. Okay, so once you click OK, it will start calculating. Now you will see the calculation time during these 15 minutes of demo that we have, like for all the different algorithms that we use. Just as you know, these algorithms in terms of time or calculation times always depend on the number of parameters that you have and the number of events. So the more events you have, the more time will take. So now I have my output here for the first sample, and as Peacock does not remove events based on the flow rate, but only on the signal acquisition, even though I have a reduction of the flow rate, there is no change within the signal acquisition. So I have 0 events removed in this case. So you have your plots right here that you can check, and everything is fine. The signal is stable overall during the acquisition for this sample. So at this point, I have 2 options. I can either go one by one, so I can take this node and move it onto my next sample, or I could just drag and drop it onto the group. That's up to you. Which one do you prefer? I'm just gonna proceed with the next sample. Now, one thing to mention as well is that once you give the start to Peacock to run on one sample, or in general for algorithms to run on one sample, you just wait that it finishes, okay? So don't try to restart or start the algorithm on a different sample, because it will try to calculate first the first one and then the second one. So just wait. My advice would be just wait for that. For some of you that may want to use version 11, this is in version 11, the quality check is a step that is included in the workflow. So you can find it right there. And it has in terms of calculation, the same statistic as Peacock. So it's a Flow AI based, but with the statistics, the MED, mean absolute deviation calculation from Peacock. So it's also a good option there. Okay, so now we have our events right here, our good events, 10%, 100%, 99%, 95%. Overall, a pretty good output, I would say. Like, there is not that much removed, or not that much that we can worry about. Of course, if you move on to your layout editor, you will find what was removed and where. So basically, in this case, what we have is, it's true that we have a drop of the flow rate, but this causes as well an alteration of the signal. So that's why I have the removal of my events right here. Okay, at this point, you can choose to export your files. So you can, if you want to start with 100% of events from each file, you can, from each population, you can choose, you can right click and you can choose export concatenate population. And in this case, you can just assign a name, call it, for example, QC, export good events, and you will have a file name example here, and you can proceed. So the reason why I'm recommending that for for some users is that you may have some cases like this one where you have 95% of events. So when you start gating under 95% of events, of course, your statistics then will be related to the total of 95%, 95.3%. So it will not be related to 100%. So for an easier calculation or evaluation later on, you can export these as a new FCS file, as I showed you, and then facilitate your calculations. Now, I'm not going to do that just for sake of time, but what I want to do is to start clean up my samples. So basically remove my irrelevant events. So we have done compensation, transformation, QC, removal of irrelevant events is another important step. So what I can do, I can take my my files, my samples here, and what I was mentioning before, the reason why I do not remove marginal events is because I do this gate on physical parameters, which anyway removes my marginal events. What are the marginal events? Are all the events that you see squished here on the axis. Okay, so within my cells, I can then take at least my singlets. Now, these are stimulated cells, maybe a little bit bigger. So if I don't want to lose my stimulated cells, I just make this 8 a little bit bigger, and I apologize for my voice. So within my single cells, I can then take my live cells. And again, if you use a live embed, this will help you a lot. So you can exclude dead cells because algorithms do not know the difference between live and dead cells. Okay, so within our live cells, I can then, I do have a dump channel as well. So the more you can exclude, the better it is if you're interested in one specific population. Or to exclude everything that you don't need. So for example, with this dump channel right here, what I'm doing is actually taking all the cells that are now positive for CD3, CD56, 19, and 20. So I can actually exclude all the positive cells for these markers right here. And finally, I have a last gate to create on my DR cells, which will show me the stimulated cells. Okay, so I will just gate on DR versus CD3 and call these cells DR positive. That's what I want to characterize. I want to characterize my DR positive cells. Now, if you are not familiar with this, you can actually use this tool right here. So once you apply your gates to your to your next samples, okay, I can do this. And again, you can work on a group and do everything at the group level. One thing I recommend you to do is to remove this node right here, so you will avoid recalculations every time. And if you apply that to a group, it's easier because you just remove it once. So now I have my DR positive populations right here, and I can go on to the next step. So I've cleaned up my data. I've pre-processed, let's say, my data. There is still one more thing to do, which is annotation and concatenation before we actually go into high dimension and into dimensionality reduction. So annotation, what I want to do, since I want to see differences between two conditions of stimulation, I actually want to label my samples with the correct condition of stimulation. So for that, I can add a keyword. This keyword can be my stim condition. Okay, and so the stim condition, please, when you add keywords, add numerical values except for 0. So this will be my condition 1, and this can be my condition 2, which is basically the non-stimulated or stimulated. Now that I have labeled my samples or annotated my samples correctly, I can move on to the concatenation step. So I can take the same exact populations from all of my samples, and you can use the right-click, select equivalent nodes for that. These will select automatically all the nodes that have the same name and are at the same level. And then you can go on to File, Export Concatenate Population. At this point, I want to concatenate my files, and I can also choose to include the same number of events within my concatenated file. And as you can see here, I have different number of events for my DR positive cells. So going from 100,000 to 22,000. So if I want, I can compare the same number of events within each DR positive population. So I can say, okay, just take 10,000 events from each of my DR populations. I can assign a name to these. And since I used a keyword to discriminate my conditions, I can add this keyword as an additional parameter in my workflow. So right here, you can choose additional parameter, and you can select your stim condition keyword. Okay. So then when you concatenate, you can choose to open the new file onto a new workspace or onto the existing one. Up to you, which one do you prefer? I'll go with the existing one again, just for sake of time. And now I have my file here. This file has 40,000 events, and these 40,000 events represent 10,000 events from each of my DR positive cells. If I want, I can make a new group just for this file, call it high dimensional, and just move this one right here so I can keep my things separated. Okay, now that I have my file, and if I open up a plot and I scroll through the parameters, I will see that I also have a stim condition parameter right here. And this will be stimulation condition 1 and stimulation condition 2. So I now can gate on this. So I can call this one non-stim. And I can call this one stim. Okay. If you have multiple samples, there is a faster way to do that. You can go on histogram here, right click and create gates on peaks. This will create peaks gates automatically. Okay, so now I have my conditions, non-stimulated and stimulated, and now I can run dimensionality reduction. So when you go into your workspace, you can find tSNE right here. And by running my tSNE, what I'll do, and we connect with the question that I had before, I actually remove my physical parameters and I remove my parameters that I used already for gating, such as the variable marker and the dump channel. Eventually, you could remove the DR as well, but I feel DR can give us more information discriminating the unstimulated versus the stimulated. And there are several options here. So there is another webinar where I go into details of what are these parameters. It's called Beyond Conventional Analysis. So if you want to go deeper into that, please check that webinar or any other webinar that has tSNE. But if you want to know the mathematics behind each of our algorithms, there is always a reference to the paper. This one is from, so I'm using tSNE, which is the optimized tSNE algorithm that was developed by Anna Belkina in collaboration with our engineers. And there is the reference right here. So I will start running and I see there is one question. It is okay that the color of the comp matrix grid is different for the concatenated file. Yes, it is okay because I'm concatenating different files. So it's fine that you have a unique compensation matrix in this case. Okay, so now I have my dimensionality reduction. I have my new dimension, tSNE2 and tSNE1. I have several options to analyze this data. I will just show you one option just for tSNE because I want to go into clustering. So one option to analyze your tSNE or to have a nice visual of your tSNE, which is something that people always love, is to drag and drop your tSNE onto the layout editor, right click, and then you can use the make multigraph overlays to show multigraph color mapping. So what we are doing is basically placing a heat map for each parameter on our tSNE, and so we can see where on our map our parameter is expressed. Okay, so I can say, show me a heat map for each of these markers right here and place it on top of our tSNE. And here you go. So now you have the heat map tSNE, where we can see, for example, where are our CD14 cells or our IL-1 beta cells, and this expression is always related to the background. So whatever you have in the background will dictate the level of expressions, okay, the color, basically. But doing dimensionality reduction is not actually enough when we want to analyze the data in a less biased way. So we can take advantage of clustering. So in this case, I not only reduce the dimensions, but I actually ask an algorithm to find the clusters for me. So within the plugins, I can choose Xshift for that. Okay. And in this case, even for Xshift, I will say, do not use the variable marker, do not use my my dump channel, and you will see that the parameters underneath, okay, the values of these parameters, number of nearest neighbors or distant metrics, are actually changing automatically based on the number of parameters that you set. So you actually don't want to worry about that. The subsampling limit, it's basically the number of events that is taking to calculate your clustering, and it's 40,000. But if you do have more events, like 100,000, you can always reduce the number of events for clustering, in this case, by using Xshift, just by defining here, which is the number that you want. So I will click OK, and you will see that Xshift is really, really fast in defining the number of clusters. Okay, now before we go into the clusters of Xshift, I see that there is a question. I had been working on tSNE on my dataset. I have 107 samples in different folders. I have done tSNE analysis on those different files. When I try to concatenate all the files to get one single map, it fails. How can be overcome? There are several problems there. So first thing, you should have all your samples into the same folder. So make sure you have your FCS files into the same folder. Load your FCS files into your workspace, and then they are all in the same workspace. Once you want to concatenate that, one thing you need to make absolutely sure is that when you export concatenate, now just to give you an example, okay, when you do concatenate, this destination folder right here exists. So one of the major issues is that FlowJo in general, FlowJo cannot find the folder because the folder is not there, or because the location is wrong, or because you're trying to save the file on an external drive or in a folder that actually was deleted. So just please make sure that you actually do have your destination folder set correctly. I'm pretty sure that could be your issue. Okay, so now I have my clusters. Xshift was able to find me 10 different clusters. I have now the option to explore these clusters or to first validate the quality. So there are several ways you can look at your clusters. The first one could be just overlay them onto your tSNE map. Okay, so you can take your tSNE, you can take your clusters and just do the overlay. So now we see our clusters right here. This could be one way. Another way is just open up your cluster and look at the expression of each individual marker one by one. And I would now recommend that. And another one is by using Cluster Explorer. But as we were mentioning before actually phenotyping our clusters, we want to make sure that the quality of our clusters is actually good. So you can run Euclid to evaluate the quality of your clusters and to have an idea. So if you go under plugins, you will find Euclid here. And as I mentioned before, it will give you two statistics based on which parameters it needs to check. Okay, so again, I will give all my parameters except for the parameters that I use to gate. And of course, this one needs to be the parameters that you used for clustering. And then I will tell him, check my clusters coming from Xshift. I know I'm out of time, so I'll try to do everything. Now it will take a few seconds, really not that long to calculate. Here we go. Okay, so now I have a modality score right here. Okay. So now I have a modality score on my left side and a Taylor index right here on my right side. So how do you look at this map, at this matrix right here? Basically, the darker is the color, the more similar to clusters could be. The lighter is the color, so the higher is the value. And this is a value for basically indicating how different your clusters are. So ideally, my cluster 1 is really different from my cluster 9. as you see here, but then when I look at my cluster 8 and cluster 9, they're possibly really similar, even more similar cluster 6 with cluster 9 eventually. So then I can go and check if they're really similar or not based on the expression on the marker with the next tool that I will show you. On the left side instead, you will find your modality score. So basically these informations are telling me that the higher is the value for the modality score, the higher is the probability that this marker doesn't have a unimodal distribution, but may have a bimodal or multimodal distribution, indicating that eventually cluster 1 is not a good cluster because of the different modality for the distribution of TNF, it may probably be needed to be divided into two different clusters. So again, if you want to go deep into, or if you want to learn more about Euclid, please check the webinar on post-clustering analysis from my colleague Ioannis, who covers this tool really nicely. So now, just to give you an example, let's check if really the cluster number 6 is similar to cluster 10, not 9, 10. 6 and 10. So how do I characterize my clusters? You can use Cluster Explorer. It is embedded into FlowJo. So I can just go on to Cluster Explorer and say, which clusters do I want to analyze? In this case, I have the ones from Xshift, which are the markers that I want to look at. And if you do have a dimensionality reduction parameter, you can use that as well. So when you accept, you will see, you will be prompted with many plots, really nice. Okay, so what I have here is different plots that show me the cluster size. I have a control panel, I have an overlay with my tSNE map for each cluster, and I have a line chart. So we mentioned we wanted to see if cluster 6 and cluster 10 are really similar. So what I can do, I can select cluster 6 from my bar chart, for example, and compare it with cluster 10. And if you look at it, actually, there are several ways you can look at it. The first one is by using the heat map, for example. So in the heat map, I can see that it's quite similar for most of the markers except for TNF. Indeed, when I go on to the line chart, I see that actually one is not expressing TNF and the other one is. Now, if I want to make sure of the actual scatter of that, I can have an extra 2D plot. Okay, and I can visualize my TNF on that. And you see that one is actually expressing TNF, the other one is not. If you want, you can change as well the colors of your clusters. Okay, so I can have this one yellow, for example, or blue. Okay, you can click OK. That now I have it in green. Okay, so how do we analyze these clusters at this point? So it's true that Euclid gave me an idea, but then it's always important for you to double check all the results that you get. So once we check that, we can then characterize our clusters. So again, you can use the bar chart right here to see how big is a cluster. You can use the heat map to see what is expressed on the clusters, but most importantly, you can use this line chart right here to select, for example, or to filter out, for example, all the clusters that have high expression of IL-1 beta. You can literally gate on that. And then if you want extra parameters or a combination of markers for that, you can say, okay, within these clusters that express high levels of IL-1 beta, show me the ones that express also TNF at the higher levels. And now you see that there are two different clusters expressing IL-1 beta and TNF. And maybe if I'm interested in one specific thing, I can say, okay, just show me the ones that do not express CD14 or do express CD14, for example. Okay. So so overall, this is how you can characterize your clusters. And again, there are two different questions that you can ask. You may be interested in the expression, in finding a cluster that has specific markers expression, or you may be interested in looking at how clusters are changing over conditions. So in that case, since we created the non-stimulated and stimulated condition as gates, what we can do, first of all, in our control panel, we actually will have the ability to look at the non-stimulated sample and the stimulated samples. And as you can see, like the distribution of our cells on the tSNE map, it's quite different. So they are different for sure. There are differences from non-stimulated to stimulated cells. But the last thing I can do if I want to have numbers, actually, I can go on to options and I can add nodes as columns. So I can say within my heat map, just add my non-stimulated and stimulated condition as an extra column. Now, what this is telling us, if we hover over, we will see the number of events and the frequency of parents. So it's basically telling us that cluster number 1 is expressed when I stimulate the cells. Vice versa, cluster number 2 is present when cells are non-stimulated, and then there's a reduction, so the frequency of parent is not really high in my stimulated condition, meaning that cluster number 2 is mostly coming from my non-stimulated cells. Okay, so that's overall how you can generate an analysis. Remember, you can take all of these, you can copy the image or copy the content and do extra statistics after that. So I see there is one question, and I know we are 12 minutes over. If we see that two clusters are similar, how can we create a new cluster composed by the previous two? That's a beautiful question, how you can do that. If you see that two clusters are similar in Cluster Explorer, now, I don't know if we have, yeah, these are not similar, but eventually, okay, let's say you want to combine two or more clusters. If you select them on your, either on the line chart, on your heat map, or on your bar chart, you can go on clusters and you can choose merge. So then when you merge the selected, you will get one cluster made out of the two clusters that you merged, two or more clusters that you merged. Then I see another question. If you return to the dataset to work in greater detail on the line chart by rerunning the Cluster Explorer, will the results be the same? The results from Cluster Explorer, as long as you do have the same clusters in your workspace, will always be the same. So Cluster Explorer runs based on what you have on your workspace. The moment that you, let's say, rerun your Xshift, or you have a new run of Xshift or a new run of FlowSum, you can pick whatever results you want for Cluster Explorer. So the advantage is that is automatically updated because you run it every time. So now what happens is that if I close this control panel, my Cluster Explorer is closed. And so I do not have a node for Cluster Explorer. That means that if I rerun it now with the same details, I will have exactly the same results. Different colors, but overall the same results. Other questions? I know we are 14 minutes over time. I'm sorry, I will always run out of time. I speak too much. So just for you to know, this webinar being recorded will be available on the website in, I believe, a couple of days or something like that. So in case you want to rewatch it, or you need to have extra information, or you just want to rewatch something else, just go on the website. If we need the frequencies of the clusters for each sample, how can we obtain that? So once you have answer live done, so once you have your heat map and you want the frequencies of the clusters per condition, I believe. In that case, if you add nodes as columns, non-steam and steam, okay, done. What you can do is copy the content of this heat map. And so then you can paste it into Excel and get your MFIs for the, for the markers and the frequency of each cluster for each condition. Thank you. Can you recommend a specific webinar for embed? Okay. Okay, before I recommend a specific webinar for embed, I got another question. But if you want for each sample and not for condition, so you get your frequencies for everything you gate on. So if you want for each sample, it means that if you do have multiple samples into your non-stimulated condition and you do have a keyword to characterize each individual sample into that keyword, for example, if I had patient ID, okay, then I could gate within my non-stimulated condition each patient ID, and then here I could actually visualize under my non-stimulated condition patient ID 1, 2, 3, 4, 5. So that's how you get your frequencies. So it's important if you want something to create a keyword for that. A keyword needs to be created for each of your variables. If you have multiple samples, multiple patients, one keyword for your patient, multiple conditions, one keyword for your condition, multiple time points, one keyword for your time point. Okay, now embed webinar. I'm 99.9% sure that if you go under learn and check for, I think it was John Queen. Okay, T-Rex, MEM, and embed. Here we go. So there is this one that it's combining actually T-Rex, MEM, and embed. T-Rex is is helping you to do, let's say, a combination of dimensionality reduction and clustering when you have two different conditions. So it's like a pipeline. MEM is for labeling your clusters that you obtained, and embed, as I mentioned before, is to embed your results into new samples. But technically, if you just type here embed, wait, it should actually give you whatever embed has, whatever is present. Yeah, here it is. So there is also one from Veronica, embed sum and flow sum. So one from Nicholas, depending on which one do you prefer. So just remember, the website is where you will find most of your answers to. Okay, so if there are no other questions, then I let you go. I thank you very much for staying with me this hour and 20 minutes. Again, many of the webinars are on the website. Just look for what you're searching for. Use the search area right here. If you do have any question, do not hesitate to reach out to me. I'll be super happy to support you. Okay. So thank you so much, everyone. I wish you a pleasant rest of the day, and I'll see you at the next webinar eventually.